Today I'm going to deal with digital electronics. See, this is a digital electronics. Okay. Now what I'll do is I'll take this one and here I'll take this color. I'll choose around this green color. Now the digital electronics. Now I'll teach a digital electronics. Okay. In this, previously we discussed about number system. Number systems. Now in that we have seen binary number system, and second is octal. Anyhow, this is a decimal system, and the hexadecimal number system. Hexadecimal number systems. And we have the conversions from binary to octal, binary to decimal, and binary to hexadecimal. And similarly, we converted this octal to binary, and octal to decimal, and octal to hexadecimal. And in this one. And next is in here, we'll see the overview of this my lectures. See, binary logic and gates. So what's a binary logic and gates? In that, see, we'll see the Boolean algebra and their basic properties and algebraic manipulations and standard and canonical form or representation of binary Boolean equations. What is a min terms and max terms, canonical form, and SOP. This SOP means sum of products and product of some standard forms. And next is a Karnaugh maps, K maps. This is simply called as a K map. And 2, 3, 4 variables and 5 variables K map. Simplification using K map. And next K map manipulation and implicants, prime implicant, essential prime implications, and what is the importance of don't case and more logic gates. We'll see one by one. And next is the first one is a binary logic. Binary logic, it deals with the binary variables that takes a two discrete values, 0 or 1. 0 or 1. It takes a two discrete values. And three basic logic operations. Three basic logic operations are there. This is AND, OR, and NOT operations. We'll see one more. And binary and logic variables are typically represented as, see, binary variables or logical variables are typically represented as A, B, C, and X, Y, Z. Even you can also write a P, Q, or S, whatever it is. There is no limitations. There is no the thumb rule. There is no any thumb rule to choose A, B, C, or X, Y, Z. Any variable which we can assume. That's not a problem. And next one is a binary logic function. See here, how the logic function is represented is this f is a function of variables and equal to expression will be there. See here in this variable, the set of binary variables will be there. Set of binary variables. Set of binary variables. Previously in first slide, what we assumed here is binary and logical variables are typically represented as A, B, C, X, Y, Z, P, Q, R, S, whatever it may be. And next one, this set of binary variables, F is a binary value and expression. Expression contains a logical operators, logical operators like place, dot, and this prime. This prime can also be represented as bar. bar, complement, and variables and constants may consist of zeros and ones, and groupings and parentheses, and this grouping. An example of this Boolean function, Boolean logic function is, you see, f of a comma b is equal to a prime. This can also be written like this: a bar dot b plus b bar. This can be written like this. Otherwise, simply he written like this. This is a prime b, and automatically ఇక్కడ b dot ఉంది అనుకోవాలి, సరేనా? Next, this is b bar, b prime. This can also be written like this. See another example: g of x comma y comma z, x dot x plus z prime. But this can also be written like this: x dot parenthesis y plus z bar. This also can be written like this. And next one is, and basic logic operations. Logical operations, logical operators, and logic operators. There are three different operators are there: and operator, or operator, and not operator. These they are very important. And this a binary means it requires a two variables. Two variables is required. Here only one unary means one variable, so it operates on one variable, whereas and or not operates on two variables. So that's why it is called as a binary operators, and this is a unary operator. Not is unary operators, and or operators are called as binary operators. So here, this is a logical function f of a comma b is equal to a dot b, means and operation. F is 1 if and only if a is equal to b is equal to 1. This is a expression, this is a definition of this dot symbol. So this can be this a and b. This dot is and operator is represented by dot, and or operator is represented by plus, and not operator is represented by bar or prime, like this. Next, CSG of a plus b is another logic function, is equal to a plus b. Means this can be read as a or b. So g is 1, the function g is 1 if either a is equal to 1 or b is equal to 1. If a is equal to 1 or b is equal to 1, in that situations. And another function h of a comma a is a unary operator. Only one variable is there, observe here, and remaining these two functions, two variables are there, so therefore binary operators is required. And this a prime, h is this logical function, h is equal to 1 if a is 0. So this is a complementary function, not operation. If it is 0 becomes 1 and 1 becomes 0 in this case. Next one is basic logic operations, logic operators. And one bit logic and resembles a binary multiplication. One bit logic and resembles binary multiplication, same as binary multiplication. 0.00. Next, 0.1, 0. Next, 1.0. This can be read as 1 and 0, 0. 1 and 1, 1. That's why this and is defined as the function and will become 1. The function of and will become 1 only when all the binary operators or binary variables are equal to 1. And one bit logic or resembles a binary addition. It almost resembles like a binary addition except for one operation. See here, 0 plus 0 is 0 and 0 plus 1 is equal to 1. Observe here, this is not a plus, this is or. We have to read it as a or. E or 1 is equal to 1. Next 1 or 0 equal to 0. Sorry, 1. Next 1 plus 1. See here, or 1 bit logic or resembles a binary addition, right? Except one operation, and this operation is that is. Except this operation, all these three operations is resembles like a binary addition. Now see 1 plus 1 in binary addition it is 1 0, whereas in a or operator it becomes 1. 1 plus 1 1. So that's why this or, the definition of or gate is the or function will become 1 only, not only if either of the binary variables will become 1. See here both are zeros, output is 0. Any one of binary variable is 1, so therefore output is 1. Any one of binary variable is 1, so therefore output is 1. Next, and both are 1 1, it become again 1, either of the one or both. In that cases it becomes logic of OR gate will becomes 1. So therefore like this. And next another is, next one is a truth table of for logic operators. And truth table tabular form that uniquely, sorry, this is q, that uniquely represents the relationship between input variables of a function and its output. Tabular form but uniquely represents the relationship between input variables and its output. See here two input AND gate is there and two input OR gate. Other inputs A and B are the inputs. A and B are the inputs. Color, what color will choose? Should I choose this? A, B are the inputs and its output function of output is A dot B. This is the output of AND gate. The output of AND gate A dot B represented as A dot B. And what are the possible combinations of input? Either maybe 0 0, ఇది 0 1 9 ఉండొచ్చు, నెక్స్ట్ 1 0 9 ఉండొచ్చు, 1 1 9 ఉండొచ్చు. తీసుకోండి. Now here we know the definition of AND operation, right? So what is when the function AND function will become 1? Only when both the inputs or both the binary variables or so therefore output will become 1. This is 0, remaining all is 0 0 0. Similarly, in a two input AND gate is there and two inputs are A and B are the two inputs, and their possible combinations are two binary literals are there. Their possible combinations are maybe 0 0, 0 1, 1 0, 1 1. Beyond this probable, there is no further probables are there. So there in situations when A is equal to 0, B is equal to 0, output of OR gate will become 0. If any one of the input is 1, so therefore output of OR gate will become 1. Here 1 is there. 1 plus 1 is 1, right? OR operation, binary or logical OR operation resembles the binary addition. But here, except this condition, 1 plus 1 in a binary addition it is 1 0. Whereas in an OR operation 1 plus 1 is 1 only, not function, not operator. A of if and 0, this is 1 and 0. C is a complement function. If input is 0, the output will become 1. If input is 1 and output will become 0. Simply. Next, truth tables. Question: Let a function f of parenthesis depends on n variable. N variable. How many rows are there in the truth table of f? See here, what he is asking is f of some here x comma y comma z comma and so on up to n variables are there. See here, we have seen if only one variable is there and 2, either it is 0 or 1, so therefore it becomes a 2 power 1. If two variables are there, so just now we have seen this becomes 0 0 0 1 1 0 1 1. So therefore how many? 4. This 4 is a 2 power 2. Similarly, if three variables are there, then how many possible combinations? 0 0 0 A B C 0 0 3 variables 0 0 0 0 0 1 0 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. See 1 2 3 4 5 6 7 8. So 8 means 2 power 3. Similarly, if n variables are there, so therefore how many rows will be there? 2 power n. So 2 power n rows, since there are 2 power n possible binary patterns, combinations for n variables. Binary patterns and combination for the n variables. Next one. This is very important. And now so we'll see the logic gates. Logic gates. So a logic gates are abstraction of electronic circuits components that operate on one or more input signals to produce output signal. Logic gates or abstractions of electronic circuits, electronic circuit components, that operates one or more input signals to produce an output signal. And two input AND gate. This is a symbol of AND gate. Something looks like a D. This is symbol of AND gate. And these A and B are the two inputs, and F is the output of AND gate. Whereas the two input OR gate, A is a one input and B is another input. It's something looks like a orange this shape. This is a symbol of OR gate. And this logical expression is A plus B, G is equal to A plus B. And logical expression for AND gate is A is equal to A dot B. Similarly, NOT gate. NOT gate is also called as a inverter. See here, if one input is there, only unary operator, not operator, and H is output, where H is equal to A prime. Where A is equal to means this can also be written like this. Previously I said A prime can also be written as A bar. In some book it is mentioned as A prime, and some books it is A. In the timing diagram, see here, consider this A, this is a 1 and this is a 0th case, and this 1 1 0 in this condition. This is an input signal. This should be like anything because this is a predefined, and B signal will be there. If it is AND operators, here A is equal to 1 in this between T0 to T1 interval of time, A is 1 and B variable is 0. A is 1 and B is 0, so therefore output of AND gate is also 0. Next, in this case, A is equal to 0 and B is also 0, so therefore output of AND gate is also 0. In this case, A is equal to 0 and B is equal to 1. In this case also output of AND gate will become 0. When both the inputs are 1, B is also 1. So therefore output of this AND gate will become 1. Next in this case, A is 1 and B is 0, suddenly it becomes 0 again, and so on. Similarly for OR gate, see here A is 1 and B is equal to 0, so therefore output of OR gate will become high. So therefore high. And both are 0 0, so therefore output of OR gate will become 0 and 0. And any one of the input is 1, so therefore output is 1. Any one of the input is 0, 1 1 1 and 1 1 is also output of OR gate is high everywhere. Similarly, see here this A complement. So what is A? This is, if A is 1, A complement will become 0. And see here both 0 0 are there, in this case it becomes 1. And here completely 1 is there. And similarly we can also write B complement. We can also write a B complement. See this B is there, 0 0 is there. So therefore we need to write 1. And both are 1 1 is there, B. So therefore in this 2 interval of time it becomes 0. And remaining 0 is there, so therefore logic is 1. The complement of the logic like this. And combinational logic circuit from a logic function. Here is a combination of logic circuit from a logic function. We'll see the question. Consider this a logical function. Okay. Now, combinational logic circuit can be constructed to implement F by appropriately connecting two input signals of logic gates. See here in this, A prime is there, A prime. So we require one NOT gate. And this is input is A. Here it become A prime or A bar. Next plus symbol is there. Let it be. Next another main term or let another term is there. This is B dot C complement. So therefore B is directly connected. And C is there. C should be complement. Complement. And next. And these two dot operator. Dot operator means and this output next third is the A prime and B prime. A is already got, I got A. A already I got, so therefore from this A complement, right? A complement, I'll take here, this is A complement, and next B complement. So I'll take another variable, I'll use this complement symbol and like this. So dot means and. Now we know this output and this inside one OR operator is there, OR operator is there. So I'll combine all these three outputs. One A complement and this output of this. All are OR operator means OR symbol. Like this, simply. See here circuit inputs from function variables A, B, C and output functions is F from this equation and logic gates from the logical operations. We'll see here. What he is given is see here f of we have to take this and dot Here f is given a comma b comma c is equal to e prime plus b dot c prime or c bar plus a bar dot b bar. This is a function and we need to implement with the logical function. So here this is a and a prime means a complement, so therefore input is a and this becomes a bar. Next consider this a and b bar, so b and b complement and these two, this becomes a b and these two complement each other, these two, this is a bar dot b bar, so here AND operation will come this. Next here b and c, this is a b, already I know I have a b wire, I'll take from here b and c bar, c bar means I'll take another complement AND gate and so b, this is b and this is c bar, this is c bar, b dot c bar second term, so therefore I'll require another AND gate. Now see here a bar, sorry, a bar plus bc whole bar, here this is b dot c bar, c bar and this is a bar dot b bar and this is a bar, so therefore a bar plus b c bar plus a bar b bar, all these three OR gate plus or gate plus indicates OR gate. This is f function. We need to represent like this. So here now here combinational logic circuit from a logic function. In order to design a cost-effective and efficient circuit, we must minimize the circuit size and propagation delay, time required for the input signal to change to be observed in the form of plan. See, observe the truth table of this one. Previously we consider this and we represented its diagram also, and in this one g plus g bar. Truth table of f is g are identical and f and g are identical. See here f is there and we'll consider we'll derive a truth table first. Presentation, here we'll take another this one and here what the function is, f of a comma b comma c is equal to a bar plus b dot c bar plus a bar dot b bar. This is a function. How many variables are there? Three variables, a, b and c. How many possible combinations? If three variables are there, how many different rows will come? Here 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So 8 possible combinations. Here in first term is there only a complement. What is a is there and its complement. If it is 0 is there, 1 will come. 0 1 0 1 0 1, remaining all 0 0 0 0 0. And see here first row and its complement. Its complement will become like this. Next, another b is there and c bar, b dot c bar. So we want C bar, right? C bar means what is the C variable? 0 1 0 0 1 0 1 0 1 0 1 0 1 is there. So its complement will become 1 0 1 0 1 0 1 0 1 0 1 0 and like this. And now we got B and C bar, and these two AND operations will come when only when their B dot C bar. B is 0, C bar is 1. So therefore become 0. When both are 1 1, it will become, so is become 1. See is B is 1 here and C bar is 1. So therefore output will become 1. Next 1 0. So it becomes 0. Next 0 1. It become 0. Next 0 0. It becomes 0. Next 1 1. It becomes 1. Next 1 0. It becomes 0. Next one is A I got A complement and I require a B complement to solve this A bar and B bar. So I write a B complement and B is this. Here 0 0 will become 1 1. Next 1 1 will become 0 0. Next 0 0 will become 1 1. Next 1 1 will becomes 0 and 0. Now we'll got A bar dot B bar. See here I got a bar. Now it is B bar. And in between AND operation is there. When both are 1, it becomes 1. Both are 1, it becomes 1. 0, 0, 0, 0, 0, and 0. Like this. This is a truth table representation. So truth table representation of any logical function. So truth table representation. And next one is, now we'll go back to this slide, our presentation. Now look at here and start linking my pen. It becomes here. And another is Z is there. Is this Z variable is given Z is equal to A complement plus B dot C bar. B dot C bar. And truth tables and B is same. So now consider, and we'll come back to this equation again, this from our presentation again. Here take another color. I'll take like black. Now see here, what he's saying is, okay, this total plus operation, right? Here A complement plus B dot C bar plus A bar dot B bar. Is this a total complement? Now it becomes A plus BC bar plus A bar B bar. It will become 1. Any one of the any one of the term is 1. So therefore output of OR operation will become 1. And this is also 1. And this 1 is also 1. And this is 0 here. And this is 0 here. And this is also 0 here. So therefore 0. Next 0, 0, 0. This is also 0. Next 0, 1, 0. This become 1. Next 0. And this becomes 0, 0. This is also 0. It becomes 0. Now write another here. I'll write here. Yes, here. A bar plus B C bar. B dot C bar. Now see here. So therefore summation of these two, oh sorry, not summation, this is OR operation of A complement not this one. This become 0, 1 plus 0, 1, 1 plus 1, so 1 plus 0, 1, 1 plus 1, 1, 1 plus 0, 1, 1 plus 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, and 0 plus 0, 0. Observe here, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0. And this function is same or not? So therefore what we can write is this function is same as a bar plus bc, a bar plus bc. Now we'll come back to here again, and two table of f for z are identical, same function. Use g to implement a logic circuit. ఇప్పుడు g తోటి ఇంప్లిమెంట్ చేద్దాం. ఇంతకుముందేమో ఈ ఫంక్షన్స్ తోటి ఇంప్లిమెంట్ చేసినాం, ఇప్పుడేమో జీ అనే ఫంక్షన్ ఏ బార్ ప్లస్ బీసీ తోటి ఇంప్లిమెంట్ చేశాను. చేయండి. ఇంతకుముందు మనం ఇంప్లిమెంట్ చేసిన ఫంక్షన్ ఏంటింది, అండ్ దిస్ ఫంక్షన్ ఇక్కడ ఉందా లేదా, ఇక్కడ మనం ఇంప్లిమెంట్ చేసినాం. ఇప్పుడు ఏం చేయమంటున్నాడు, ఇది ప్లస్ ఇక్కడ ఏమన్నాడు ఏ బార్ ప్లస్ b dot c bar. This is a function. So previously we proved that, and this function is same as this function. So therefore what I'll do is only I require a complement here. This is a input a and the output of this AND gate is a complement. Next b and c, this I require only b line, and c I require a complement, so therefore I'll draw with I'll take another and NOT gate, and here b dot and c bar. This is b and this is c, this becomes c bar, and this is b only. So b c bar dot means AND operation, and these two OR operation, so this becomes the z, and function f and z are both are same. Here this a bar, this input is a bar, this is b dot c bar, so therefore this becomes a bar plus OR operation b dot c bar. Now observe here, previously this is one gate number 1, gate number 2, gate number 3, gate number 4, gate number 5, and gate number 6. How many gates are required here to implement this? 6 gates. Whereas here, see here 1, 2, 3, and 4. So 4 gates are required. And these two functions are doing same work, but if we come to implementation, logical implementation using logic gates, here we require 6 gates and here we require 4 gates. And which one is more complex? Most obviously this is a 6 gates of the more complex circuit than this gates with a 4 circuit with a 4 gates. So therefore our, as a digital designer, one should design a circuit with less number of gates. That becomes a more efficient designing, more efficient design. And now here in here, if we come here again, come back to this previous slide, here it told us once here To minimize, we must to minimize. Okay, first we'll go here. So in order to design a cost-effective and efficient circuit, we must minimize the circuit size, area. We need to reduce area and propagation delay, time required for the input signal to change to be observed at the output. See, 4, 6 number of gates are there, so that definitely more time is required. Whereas if it is only 4 gates, definitely less size is required. Less size will become size be reduced, as well as the time taken by the circuit to uh, by by circuit is also decreases. This way we have to implement the logic circuit. See, he represented here. This is C. This is C bar. Here got a A. No, no, this is a B. See here, this is a B. Here a B, and this is A bar. This is a B bar. This is A bar dot B bar, and this directly A bar is connected here, and this is B dot C bar. This is function. How many gates are there? 1, 2, 3, 4, 5, 6. 6 number of gates are required. And similarly, and these two gates are performing same function with less number of gates. 1, 2, 3, and 4. Only 4 gates are required. According to E, which one is a more efficient design? Next, Boolean algebra. Very nice machinery used to manipulate or simplify a Boolean functions. George Boole, 1850, 15 and 1864 is a date, an investigation of law of thoughts. Terminology, literal. Terminology which is used in a Boolean algebra, literal. A variable on or its complement. A variable or its complement. Here, example, x is a literal or x power complement. A variable or or its complement is called as a one literal. This is a literal, is another literal. Product term. Literals connected by dot. Product terms are all dot terms. See example, x dot y is a one main product term. Is a product term. Or x bar dot y bar is a product term. Next, x bar dot y is another product. A dot B bar is another product term like this. And some term is literals connected by place. So this is A plus B, A plus B, one some term. A plus B bar, some term like this. Boolean algebra properties. This is very important to reduce any logical expression, complex logical circuits. Let x is a Boolean variable, and 0, 1, 1 are the constants. So here x plus 0 is equal to 0. X. So here in this situation, 0 is a fixed, right? Where x is a binary literal. This may be, see here, binary variable. Binary variable itself may consist either it is 0 or 1. Consider first case if only 0. 0 plus 0. What is 0 plus 0? 0. Next, 1 plus 0. 1. So therefore, if x is equal to 0, అయితే 0 వస్తుంది. If x becomes 1, it will become 1. So therefore, x plus 0 is equal to x. Whatever the value is x, that will come here. So this is called as 0 axiom. 0 axiom. And next second one is x dot 1. See here x dot 1, x dot 1. See 1 is fixed. So this x is a binary variable. It may be 0 or 1. If it is 0, 0 dot 1. If it is 1, 1 dot 1. 0 dot 1 is 1, sorry 0. Next 1 dot 1 is 1. See here? Again it becomes 0, 0 where the x is equal to 0 అయితే 0 వస్తుంది, 1 పెడితే 1 అవుతుంది. And irrespective of another variable, if x dot 1 is there, now output of this logical expression will always become x, and it doesn't care about this one, meaningless. So this is unit axiom. Next x plus 1 is there. Here also x is either 0 or 1. So 0 plus 1 will become 1. 1 plus 1 is also 1. So therefore irrespective of this 1, it doesn't have any change on this logical expression. Is 0 either 0, sorry 0 aina 1 aina, unit property, always it will become 1. See here, if it is 0, 0 plus 1, 1, 1 plus 1, it is also 1. 1 plus means this OR operation, and don't confuse with the binary addition as well as binary OR operation. X dot 0 and 1, 1 is here with AND means this AND operation. AND operation will become 1 only when both only when both inputs are 1 1. So therefore one of the input is 0, already we know. So therefore directly irrespective of another variable, another input, so output of AND gate will become 0. This is a 0 property. Next Boolean, let x is a constant, same another 5. If x plus x is equal to x, see here x plus x, say x is a binary variable, it may be 0 and 0. 0 plus 0 is equal to 0. If it is 1, so 1 plus 1 is equal to 1. So if 0 unte 0, 1 unte 1, so therefore x is equal to x plus x is equal to x only. X plus x is equal to x only. Next is here x dot x, 0 dot 0, 0, 1 dot 1, 1. So therefore whatever the x value is 0, 0 dot 0, 0. X value is 1, 1 dot 1, 1. So therefore x dot x is also x. Next x plus x bar, x plus x bar. Say consider x is equal to 0. This is 0 plus x bar will become 1. 0 plus 1 is equal to 1. Next consider x is equal to 1. 1 plus x bar is complement of x, 0. So therefore 1 plus 0 is also 1. So therefore always x plus x bar always equal to 1. Similarly, this one x dot x bar is always 0. Why? Because x dot x bar, if it is 0, this becomes 0 dot 1. If it is 1, or x is 1, 1 dot 0, so it will become always 0. This is 0 always. Next here, this is x complement x prime whole prime is there. This can also be written like this, x bar and whole bar. So therefore 2 times complement. Consider x is equal to 0 is there. Once complemented it become 1. Another and again complemented becomes 0. So if 2 times complemented means again it backs to 0 or not. Even x also, x is equal to x complement and complement another complement, and these two complements will get cancel each other, therefore leftover is x only. And duality principle. In duality principle, expression is obtained by exchanging dot with plus one with and one and zeros in it, provided that the precedence of order is not changed and cannot change x with x prime. Example, here is a this is what we need to do. X prime, here a dot operation is there, we need to place y z, y is there as it is y, and place z prime is there and write as z prime. The place operation is there, so therefore dot operation. And next x prime is there, right, as it is x prime. Here a dot is there, so therefore place. Next y prime, write down y prime as it is. Dot is there, so therefore place. Z is already z, and these two are like this. This is a duality of f of x. Duality of this equation is duality of f of x comma y comma z of logical expression. With respect to duality, identity 1 to 8. Here. Here x plus 0 x dot 1 x dual of n. See here x plus 0 0. See x as it is x as it is x, plus is there, dot 1 is there, 0 is there, is equal to x. X plus 1, dual of this x dot 0 is equal to 0, 1 is there, 0, like this. Or x plus y is equal to y plus x dot y is equal to y dot is a commutative law. It doesn't make any difference. There is no any priority of variables. And this x plus y plus z, x plus y plus y dot x dot y dot z. So associative law. Distributive law. And x plus y whole bar is equal to x bar dot y bar, and xy whole bar is equal to x dot y whole bar is equal to x bar plus y bar. These are the De Morgan's laws, is very important. Similarly, is also for n variables, it becomes individual variables. Absorption property. See here in this x, consider this equation x plus x dot y. So consider this. Now x is common, 1 plus y. What is 1 plus y? Are 1 plus x is equal to 1 always. So this becomes x dot 1 is equal to x always. This is an absorption property. Similarly, here, similarly this x dot x plus y equation is x dot x x plus x dot y x y like this. Therefore, here again x common become 1 plus y. So therefore is equal to x dot 1 plus y 1 is equal to 1. This is the x, also x. So dl. This given true by duality y. Power of duality. And see is true. So both sides are complement. No? So here, what he is saying is, and this equation is there given. So he is doing this complement here and again complement here. Both are complemented now. LHS and RHS gets complemented. Doesn't make any difference. X x bar dot Hugo process can be applied to the any formula. So the formula, if formula is valid, then its DL must also be valid. Proving one formula also proves its dual. Census theorem. This is xy and xz, xy plus x bar z, and proof is given like this. Xy x bar z, here xz is the yz is there now, in that he written y is x plus x bar. This x plus x bar 1. So any variable we can multiply it with 1. So we get the same one. Xy and x bar z. Here xyz plus x bar yz. Xy and xyz, xz bar and xy is common. This is 1 plus z. If we take xy common here, xy common 1 plus z plus here x bar z common 1 plus y. This is 1 plus z will become 1, 1 plus y will become 1. So therefore answer is xy and xy. Question to which duality. Truth table enumerates all possible combinations of variables and the corresponding functions of values. And truth table for some arbitrary functions f of x y z, f2 comma is a one function, so another function, this is another function, or three shown right here. This is f1, f2 and f3. And truth table, unique representation of Boolean function. So defined as a unique representation of Boolean function. If two functions have identical truth tables, their functions are equivalent, and vice versa. And truth tables can be used to provide equality theorems. Equality theorems. However, the size of truth table grows exponentially with the number of variables involved. Hence, unwieldy. This motivates the use of Boolean algebra. It's a use of Boolean algebra. Boolean expressions not unique. Boolean expressions are not unique. Unique ఏముండవు. Unlike truth tables, expressions representing a Boolean functions are not unique. Example: use the Boolean function. The corresponding truth tables of f comma and j comma are to right. They are identical. Thus, f of j. Algebraic manipulations. Algebraic manipulations will be Boolean algebra is useful tool for simplifying digital circuits. Boolean algebra is a useful tool for simplifying digital circuits. Why do it? Simpler can mean cheaper, smaller, faster rate. Play this one.